Imagine this. You're lying awake at 2 a.m., scrolling through your phone, and you stumble on the sentence, "We're going to send a paperclip to a black hole." Not metaphorically, not as a joke. Literally, humanity is sketching plans to launch something the size of a fingernail file across interstellar space to slam into one of the darkest, most dangerous objects in the universe. Now, I know what you're thinking. Sure, and tomorrow we'll all be riding unicorns to work. But hear me out, because the proposal isn't coming from a sci-fi writer in a basement full of Star Trek posters. It's coming from an actual astrophysicist, Cosmo Bambi. Yes, his real name is Cosmo, and yes, he studies black holes for a living. Talk about nominative destiny. His idea? Use a weapon humanity already has. Not rockets, not nuclear engines, not some futuristic warp drive, but light itself. Specifically, a giant laser. Aim it at a tiny sail attached to an even tinier probe, and whoosh, our miniature spacecraft shoots off into the cosmos at 1/3 the speed of light. That's 100,000 kilometers per second, faster than anything humanity has ever built. At that speed, if there's a black hole lurking within 20 or 25 light years of us, we could reach it in about 70 years. Another 20 years for the data to make the return trip home. You and I wouldn't be around to hear the final transmission, but maybe your grandkids' will get the notification. Imagine their faces when they check their dusty space email. New message received. Greetings from the abyss. It sounds absurd, doesn't it? But that's the thing about science. Every great leap started out sounding absurd. People laughed at the idea of flying machines, moon landings, even washing your hands before surgery. Yet here we are, casually planning a mission to send a chip the size of a thumbnail into the jaws of a black hole. And the funny part is, we've done this before. Not the black hole part, but the hole. Let's attempt something ridiculous and impossible. Remember gravitational waves? Predicted in 1916. People spent nearly a century saying, yeah, good luck with that. Then in 2015, we finally detected them. Or the first photograph of a black hole, half a century of trying, and in 2019 we got it. History is basically a series of humanity saying, this will never work, followed by, oh wow, it actually worked. So yes, this black hole paperclip project might sound like a cosmic prank, but it's dead serious, and it could change everything we know about physics. Because black holes aren't just big scary drains in space, they are the ultimate laboratories, nature's extreme test sites. The place where Einstein's equations go to the gym and either come out stronger or collapse in embarrassment. If you want to find out what space-time really is, you don't ask politely. You throw a probe at a black hole and see what happens. That's the spirit behind Cosmo Bambi's plan. And tonight, we're going to unravel it together. The ambition, the science, the absurd price tag, and the philosophy of building something today whose answers won't arrive until long after we're gone. So pour yourself some tea, turn off the lights, and let's step into this wild idea. Humanity's first attempt to poke a black hole with the tiniest stick imaginable. Stop. Do you want me to roll straight into part 2, the nanocraft concept, keeping the same style? All right, so what exactly are we sending to a black hole? A starship? A space shuttle? Maybe some futuristic interstellar-style craft with spinning rings and a crew of poets and physicists? Not even close. We're talking about a spacecraft that weighs just a few grams. Think about that. A sugar packet is heavier. A Lego minifigure has more mass. This little craft is basically a silicon chip with a whisper-thin sail attached. No rocket boosters, no fuel tanks, no comfy cockpit with cup holders. Just a microchip brain riding a kite made of light. It's called a nanocraft, And the principle behind it is both absurdly simple and mind-bendingly clever. Instead of carrying its own fuel, which is heavy, expensive, and quickly runs out, you let light do the pushing. Imagine holding a sheet of aluminum foil in front of a strong gust of wind. It flutters, it moves. Now replace the wind with an Earth-based laser, cranked up to unimaginable power, aimed at a sail thinner than a human hair. The photons streaming off that laser don't weigh much individually, but when you fire trillions upon trillions of them, they push constantly. And over time, they accelerate the sail to ridiculous speeds. We're not talking about space snails here. We're talking about 1/3 the speed of light, 100,000 kilometers per second. That's fast enough to get from Earth to the Moon in about 4 seconds. It's like strapping your phone to a cosmic slingshot and firing it into the deep night. And the sail, the sail, is a work of art. Picture something a few meters across, made of a material so delicate that if you sneezed on it, it would probably tear. Yet it has to survive being blasted by a laser array the size of a city, then cruise through decades of interstellar space without falling apart. Imagine sending a soap bubble through a sandstorm and hoping it comes out intact on the other side. That's basically the engineering challenge. The idea isn't just science fiction. We already have proof of concept in things like the Japanese Ikaros mission, a solar sail launched in 2010 that successfully rode sunlight across the solar system. That was baby steps. Cosmo Bambi's proposal? That's the equivalent of going from riding a tricycle around your driveway to entering the Tour de France on roller skates. But here's where it gets funny. Rockets are dramatic. They roar. They light up the sky. They shake the earth. Laser propulsion? Silent. Invisible. A beam of light so intense that it pushes your fragile spacecraft out of Earth's orbit like a cosmic leaf blower. You don't get flames or thunder. You get nothing. Just a tiny chip vanishing into the dark, traveling faster than anything we've ever built. And if it works, this little postage stamp spaceship becomes humanity's first true interstellar emissary, not a Voyager record, not a giant golden plaque with Beethoven and whale sounds, but a speck of silicon whispering into the void. That's the plan. A black hole, a sail, and a beam of light. Now the obvious question, where exactly do we aim this thing? Because a 70-year journey is only useful if there's a black hole waiting at the other end. And that, as it turns out, is the first big cosmic headache. So, we've got our paperclip-sized spacecraft, our sail, and our planet-sized laser pointer. We fire it up, and whoosh, the probe takes off, racing into the darkness. But here's the thing about space. Even at 1/3 the speed of light, it's still slow. Not YouTube buffering slow. More like, you will die, your children will die, and their children might be the first to check the mailbox. Slow. If there's a black hole within 20 to 25 light years, this little craft could get there in about 70 years. That's one human lifetime, if you're lucky. But that's only half the story. Because once it arrives, once it brushes past that monstrous event horizon and collects its data, it still has to send it back home. And those signals, traveling at the speed of light, will take another 20 years to return. 70 plus 20, 90 years total, nearly a century between launch and payoff. Which means the scientist who presses the launch button, the engineer who welds the sail, the technician who checks the microchip, none of them will ever live to see the data arrive. By the time Earth receives that first faint transmission, the original team will be gone, their work carried forward by grandchildren of grandchildren. It's not a project for a person. It's a project for a civilization. That's the mind-bending beauty of it. We're used to science working on human timescales. Build a telescope, point it, boom, you get results. But some discoveries don't fit neatly inside our lifespans. They stretch across generations like cathedrals in medieval Europe, built stone by people who knew they'd never see the spire completed, but trusted that someone, someday, would. This black hole mission is exactly that. A cathedral of light. Now, imagine explaining this at a family dinner. So, what are you working on these days? Oh, just building a spacecraft to throw at a black hole. Should be back with answers in the year 2115. Cue the awkward silence. And yet, history tells us this kind of stubborn patience works. Gravitational waves were predicted in 1916. It took 99 years to confirm them. The first black hole was theorized in 1783. We only imaged one in 2019. Science has a way of demanding absurd levels of faith, only to pay it back in cosmic jackpots. That's what makes this mission so intoxicating. It's not just about the data, it's about the act of planting a seed we'll never see grow. It forces us to think not as individuals, but as a species. To imagine ourselves as part of a relay race where knowledge is the baton, and we're just one runner on a very long track. But of course, there's one tiny detail we can't overlook. You can't throw a probe at a black hole unless you know where the black hole actually is. And that, my friends, is where the cosmic scavenger hunt begins. All right, so we've built the paperclip spaceship, we've got the world's most overpowered laser pointer, and we're ready to aim it. But aim it at what, exactly? Because here's the awkward truth. The closest confirmed black hole, Gaia BH1, is more than 1,500 light-years away, which is about 1,475 light-years too far for our fragile nanocraft. If we tried to send it there, the poor thing would arrive long after Earth had probably gone out of business as a habitable planet. So the only way this mission makes sense is if there's a smaller, quieter black hole lurking in our cosmic neighborhood. A stealthy one, hiding within 20-25 light-years. And astrophysicists think that's actually likely. Black holes don't always announce themselves with big, flashy accretion disks or jets of plasma. Some are invisible freeloaders, drifting silently through space, giving themselves away only by their gravitational pull. So how do you spot something that doesn't emit light, doesn't glow, doesn't shine, basically the universe's best hide-and-seek champion? Option 1. Watch the stars around it. If a nearby star is wobbling strangely, dancing like it's had one too many drinks, it might be orbiting an invisible partner. That partner could be a black hole. Astronomers have used this trick before to identify binary systems where the visible star is basically being yanked around by a dark companion. Option 2. Gravitational lensing. A black hole bends light passing near it, like a cosmic funhouse mirror. So if you're staring at a star and suddenly its light looks warped, magnified, or shifted, congratulations, you might have just found an invisible black hole sitting between you and it. But here's the catch. These effects are tiny, subtle, like trying to notice if your neighbor's porch light looks a little weird because someone placed a transparent marble in front of it while you're standing 5 blocks away. That's why astronomers need ultra-precise surveys, scanning millions of stars for faint wobbles and distortions. And that's where hope lies. Upcoming projects, next-generation telescopes and sky surveys are basically black hole truffle-hunting dogs. They'll sniff out the hidden ones. With luck. Sometime in the next decade, one of these invisible monsters will pop up right in our backyard. Until then, though, the entire mission is on pause. You can't fire your interstellar paperclip without a target. It would be like playing cosmic darts blindfolded. So the hunt is on. Somewhere out there, maybe only 20 light-years away, there's a black hole hiding, silent, dark, waiting. And the moment we find it, the countdown begins. But let's be honest, the black hole is the easy part. Finding one is just astronomy. The real nightmare is building a spacecraft so fragile It makes a soap bubble look sturdy, and then asking it to survive a 70-year interstellar road trip. That's where the engineering headaches begin. All right, we've got a target in mind, or at least the hope of one, and now we face the next hurdle, actually building the thing. On paper, a nanocraft sounds adorable. A little chip with a sail, floating gracefully through the cosmos. But space, as it loves to remind us, is not cute. Space is a meat grinder with no mercy. And this craft has to survive 70 years in the grinder. Let's start with radiation. Out in interstellar space, you're not just basking under warm starlight. You're being bombarded constantly by high-energy particles, cosmic rays, gamma radiation. It's like flying through an endless hailstorm of invisible bullets. For a microchip that weighs less than a teaspoon of sugar, that's a death sentence unless it's shielded. But shield it too much, and poof, your lightweight probe becomes a brick. So engineers have to pull off a miracle. Materials that can shrug off radiation, but don't add weight. Then there are the micrometeoroids, tiny grains of dust zipping through space at tens of kilometers per second. To us, that sounds harmless dust, right? But at those speeds, a dust grain is a bullet. For our paper-thin spacecraft, it's like driving a convertible through a sandblaster for 70 years. The odds of survival are, let's say, less than comforting. And power. The nanocraft can't carry a gas tank. It can't lug along a nuclear reactor. It has to be tiny, lightweight, self-sustaining. That means some mix of ultra-efficient solar panels, which get uselessly weak the farther you go from stars. Miniaturized batteries, or maybe harvesting energy from the environment in ways we haven't even perfected yet. Imagine trying to keep your phone charged for 90 years with no outlet, no power bank, and no upgrades. That's the challenge. And even if somehow it survives the trip, the probe has to talk back to us. Imagine being 25 light-years away, with the weakest transmitter imaginable, trying to shout across the void of space to a receiver on Earth. It's like whispering across an ocean and expecting someone on the opposite beach to hear you. That's where radio science, antennas, and clever data compression come in. The craft has to be able to say, "Hi, I'm still alive. Here's what I saw before I almost died." So yes, the probe isn't just a spacecraft. It's a miracle in waiting. A soap bubble expected to cross a hurricane. And the most sobering part? We don't even have all the technology yet. The nanocraft is more of a sketch than a product. A blueprint that says, "Here's what we'd need, please invent it." Radiation-proof microchips, self-healing materials, ultra-light communication systems. We're basically writing Santa a letter and hoping physics delivers. Still, there's something irresistible about that. It's raw human stubbornness. We've always thrown fragile things into impossible environments, ships into the unknown seas, balloons into the stratosphere, fragile rovers onto Mars. Half the time, they weren't ready. Half the time, they failed. But sometimes, just sometimes, they worked. And those times changed history. The nanocraft will be no different. A ridiculous gamble, a fragile dream. But if it survives, it could become the first little scout to touch the jaws of a black hole. And just when you think that's the biggest headache, nope, that was only the probe. The real engineering nightmare is on Earth. Because to get this thing moving, we need the mother of all laser beams. So, the nanocraft is a soap bubble with a Wi-Fi plan. Fragile, uncertain, almost absurd. But none of that matters if we can't even get it moving. And for that, we need the lasers. Now, when I say lasers, don't picture a couple of red cat toys duct taped together. We're talking about an array of high-powered beams, synchronized, pointed into the sky, focused on a sail the size of a bedsheet, thousands of kilometers away. A planetary-scale Death Star, minus the whole blowing-up planets thing. And the price tag? About 1 trillion euros at current estimates. Yes, trillion. With a T, the kind of number that makes you sit back and think, wait, how many zeros is that again? It's the cost of 10 international space stations, or every Marvel movie ever made times 50. It sounds ridiculous, and it is, but history is full of ridiculous numbers. The Apollo program, adjusted for today, cost about $250 billion. At the time, people thought it was insane to spend that much just to put a few humans on the moon. But look at what it bought us. GPS, satellites, computer advances, even the tech that powers your smartphone today. So 1 trillion euros doesn't mean impossible. It just means give us a few decades. Technology has this sneaky habit of shrinking costs while boosting capability. Right now, laser infrastructure of that size is fantasy. But in 20 or 30 years, with advances in energy, optics, and manufacturing, that trillion could drop to a billion. And suddenly, the cosmic Nerf gun looks more like a flagship science mission. Still, the logistics are nightmarish. Think of what's required. Thousands of individual lasers firing in perfect synchronization. Adaptive optics to counteract atmospheric distortion, because Earth's atmosphere loves to bend light like a drunk funhouse mirror. A ground station the size of a small country, guzzling electricity like a city. And remember, the target is a wafer-thin sail hurtling upward at incredible speed. Miss by a fraction of a degree, and your billion-dollar beam just lights up the night sky for the birds. Oh, and there's geopolitics. Because let's be real, build a planetary-scale laser array, and you can bet the military will start sniffing around. Oh, you're building it for science? That's cute. Can we also aim it at things? Cue decades of treaties, arguments, and memes about Earth's biggest laser pointer. But despite all that, the allure is undeniable. If we can crack laser propulsion, it changes everything. Interstellar missions stop being thousand-year epics and start being lifetime projects. Suddenly, Alpha Centauri isn't a dream for the 400th century. It's something you could plausibly do in the 22nd. So yes, the lasers are absurd, expensive, terrifying, politically messy. But they're also the key. The match that lights the sail. The shove that turns our paperclip probe into humanity's first interstellar scout. And here's the twist. We've already started inching toward it. Projects like Breakthrough Starshot are laying the groundwork. Which brings us neatly to the next chapter. How this crazy black hole idea isn't emerging from nowhere, but standing on the shoulders of an equally audacious plan. Here's the thing about audacious science. It rarely arrives fully formed, like Zeus popping out of Mount Olympus. It usually piggybacks on an earlier, slightly less insane idea. And in this case, that idea has a name, Breakthrough Starshot. If you haven't heard of it, think of Starshot as humanity's first serious attempt to turn interstellar travel from science fiction into, hey, maybe in our lifetime. The plan is almost identical to the black hole probe. Fire a fleet of nanocrafts, each weighing only a few grams, toward Alpha Centauri, our closest star system, 4.2 light-years away. Instead of taking tens of thousands of years with chemical rockets, these laser-propelled chips could get there in about 20 years. That's less than the time between your first cell phone and the one you have in your pocket now. That's basically Netflix binge time in astronomical terms. Of course, Starshot is still a proposal. A team of scientists, engineers, and a couple of billionaires put it on the table in 2016. They ran the numbers, drew up designs, and said, "We can't do this yet, but it's not crazy. It's just really, really hard," which in science is basically a compliment. The black hole mission takes this same playbook, nanocrafts, light sails, Earth-based lasers, and dials it up to 11. Instead of going to a friendly star next door, it's aiming straight for the most hostile, physics-bending environment in existence. It's like graduating from "let's climb Mount Everest" to "let's climb Mount Doom," barefoot, while juggling flaming swords. But that's what makes it brilliant. By standing on Starshot's shoulders, the black hole plan doesn't have to reinvent the wheel. It inherits decades of research into ultralight materials, laser arrays, interstellar communication, radiation shielding, and micro-instruments. Think of it as science recycling. And just like Starshot, the plan isn't just about one mission. It's about opening the door. The same laser propulsion technology that could fire a chip at a black hole could also fire dozens of chips at nearby star systems, scatter probes across the galaxy, even send tiny scouts ahead of human missions. It turns interstellar space into a playground instead of a prison. Now, let's pause for a second, because I know what you're thinking. Why black holes? Why not just stick with the stars? They're prettier, less terrifying, and easier to explain at dinner parties. But here's the catch. Black holes aren't just cosmic oddities. They're physics turned up to 11. And if you really want to understand the universe, how space, time, and matter behave at their most extreme, you don't look at stars. You stare into the abyss. Which brings us to the heart of it. Why a black hole is worth the trouble in the first place. So far, this mission sounds like a cosmic dare. Build a paperclip spaceship, strap it to a €1 trillion laser, and fling it into the void for 90 years. That's not exactly a pitch you'd use on Shark Tank. So why bother? Why not spend the money on something more practical? Like curing diseases, solving climate change, or maybe finally inventing a printer that works on the first try. The answer is deceptively simple, because black holes are the universe's ultimate laboratories. They're where the rules of physics stop being polite and start getting real. Think of it this way. Every scientific field has its stress test. Engineers smash cars into walls to see how they crumple. Chefs crank ovens to extremes to find out when sugar burns. Physicists, we hurl our equations into black holes and watch which ones come back in pieces. Einstein's general relativity has survived every test we've thrown at it, from planetary orbits to GPS satellites to colliding neutron stars. But those are baby weights. To really see if relativity can handle the heavyweight division, you need to drag it ringside with a black hole. Because inside that environment, space and time don't behave like they do anywhere else. Distances warp, time stretches, light itself bends into pretzels. If the universe has hidden cracks, little gotchas in its programming, that's where they'll show up. And that's not just science for science's sake. Understanding black holes touches everything: our theories of the Big Bang, the nature of dark matter, even the possibility of parallel universes. They're like cheat codes for reality. But it's not all highbrow theory. There's also something deeply, irrationally human about staring into the abyss. Black holes are the monsters of the cosmos, silent, invisible, and inescapable. Sending a probe to one is our way of saying, "We see you, and we're not afraid to knock on your door." It's the same impulse that pushed sailors past the edge of the map, that put humans on the moon, that made us point giant telescopes into the dark and whisper, "What if?" And here's the delicious irony. By probing black holes, the places where light itself vanishes, we might finally shine light on the deepest mysteries of existence. So yes, it's absurd. Yes, it's dangerous. Yes, it's staggeringly expensive. But if you want to know what the universe is really made of, you don't stay in safe waters. You dive into the whirlpool. And the first whirlpool on our checklist? That mysterious line in the sand known as the event horizon, the place where, supposedly, no return is possible. But is it really that simple? That's the next riddle. If black holes are the monsters of the cosmos, then the event horizon is their gaping mouth. It's the invisible line in space that says, beyond this, nothing returns. Not light, not matter, not even desperate text messages fired into the void. Cross it, and you're gone forever. At least, that's the textbook version. But here's the kicker. We've never actually been up close to one. We've seen their shadows, we've modeled their math, we've watched stars whip around invisible partners, but no one has ever gotten near enough to check whether the horizon is exactly what Einstein's equations predict, or if the universe has a surprise waiting for us. If general relativity is correct down to the decimal, the event horizon is exactly what we think, a one-way door. But some alternative theories, whispers at the edges of physics, suggest something stranger. Maybe black holes don't have horizons at all, but hard surfaces made of exotic matter. Maybe what we call black holes are really fuzzballs, or gravastars, or some other exotic creature. To put it less academically, are black holes the clean, elegant death traps Einstein promised? Or are they cosmic pranksters wearing elaborate disguises? That's why a probe matters. From afar, the difference between an event horizon and an exotic surface is basically invisible. But up close, you'd see distinct patterns, light bending differently, radiation flaring in odd ways, maybe even particles bouncing back instead of being swallowed. A nanocraft brushing past the edge could settle a debate that has haunted physics for decades. And think about what that would mean. If the horizon is real, Einstein gets another gold star on his cosmic report card. If it isn't, then we're in uncharted territory. New physics, a whole new map of reality. The kind of shift that happens once a century, like Newton giving way to Einstein. And the beauty of it? Our probe doesn't even have to survive crossing the horizon. It just has to get close enough, transmit what it sees, and then snap, it's gone. Sacrifice to the void, but not before whispering back the secrets of the edge. Imagine being alive the day those signals arrive. Humanity tuning in to a message from a speck of silicon that flung itself into a black hole a lifetime ago. That's not just science, that's poetry. And of course, this all circles back to one question. Einstein himself. Because if relativity cracks at the horizon, it means the old master didn't have the final word. And in science, nothing is holier or scarier than finding out that Einstein was only half right. Albert Einstein is like the rock star of physics. His hair alone deserves its own Nobel Prize. And his masterpiece, the theory of general relativity, has been strutting on stage for more than a century without missing a beat. Planetary orbits? Nailed it. The way light bends around the sun? Checked and confirmed. GPS in your phone? Works only because relativity quietly corrects the time signals. Even gravitational waves, the faintest ripples in space-time, showed up exactly as Einstein predicted, 100 years after he first scribbled the equations. The man just doesn't miss. But here's the uncomfortable truth. We've only ever tested relativity under relatively gentle conditions. Planets circling stars, neutron stars colliding. Sure, they're dramatic by human standards, but by cosmic standards, they're warm-up acts. Black holes, though black holes are the main event. The heavyweight championship. Inside their gravity wells, space-time isn't just curved. It's folded like origami and stretched like taffy. If relativity is going to crack, if it has some tiny flaw hidden in its DNA, this is where it'll happen. And finding that flaw wouldn't just be nitpicking. It would mean opening the door to a new era of physics. Because right now, relativity is king of the big stuff, planets, stars, galaxies, while quantum mechanics rules the small stuff, atoms, particles, subatomic chaos. The two theories don't play nice together. They're like divorced parents forced to share custody of reality. What we really need is a unifying theory, one set of rules that works from quarks to quasars. Where might that missing link hide? At the edge of a black hole, right where relativity is pushed past its breaking point. That's why the probe matters. Because brushing near the horizon could reveal effects relativity doesn't predict. Gravitational redshift so intense it scrambles light in ways we've never seen. Time dilation so severe that a few minutes for the probe could equal decades for us. Quantum fuzz creeping into the smooth fabric of space-time. Think about that for a second. A paperclip-sized craft could become the referee in the biggest fight in science history. Einstein versus the unknown. The heavyweight rematch we've all been waiting for. And here's the twist. Whether relativity holds up or collapses, we win. If it holds, we gain confidence in the foundation of modern physics. If it falters, we get clues toward the next great leap, a physics 2.0. Either way, the abyss answers. And that's just the headline. Because while Einstein takes center stage, there are a dozen other mysteries lurking in the wings, waiting to be uncovered if we can just get close enough to listen. All right? So settling the Einstein debate would already justify the whole mission. But black holes aren't one-trick ponies. They're jackpots of mystery, slot machines of physics that pay out in strange and unexpected ways. If our probe gets close enough, it won't just answer the event horizon question. It could open an entire buffet of discoveries. Take gravitational redshift. We've tested it on Earth, with clocks ticking slightly slower at the bottom of mountains than at the top. Cute, but near a black hole, the effect goes wild. Light itself gets stretched, reddened, as if the universe is pulling on it like taffy. Measuring that up close would be like cranking Einstein's experiment from a polite violin solo into a full heavy metal concert. Then there's time dilation. Near a black hole, time doesn't just slow, it practically collapses. For the probe, minutes might pass. For us, years. Send it too close, and it becomes the loneliest tourist in the universe, snapping selfies at the horizon while humanity fast-forwards a century waiting for the uploads. And what about accretion flows, the rivers of matter spiraling into the black hole? These flows are hot, violent, magnetic, turbulent, beyond comprehension. They glow in X-rays, twist space with their magnetism, and sometimes spit out jets of plasma that stretch light years across. A probe nearby could measure their turbulence, their particle storms, their magnetic gymnastics in real time, or consider quantum effects. There are theories wild, daring ones that say the edges of black holes might shimmer with quantum-scale fuzz. Hawking radiation, exotic particles, phenomena we've never seen in a lab because Earth just isn't extreme enough. A close pass might sniff out hints of that fuzz, finally confirming or killing off decades of speculation. And then there's the catch-all category, things we don't even know to expect, because that's the secret beauty of science. The most transformative discoveries are often the ones we didn't plan for. Columbus wasn't looking for America. Penicillin was an accident. The microwave oven started as a melted chocolate bar in a physicist's pocket. That's why throwing a probe at a black hole is so intoxicating. You can write down a shopping list of physics goals: redshift, time dilation, accretion flows, quantum fuzz, but the real treasure is in the blank spaces, the surprises, the curveballs the universe throws at us when we dare to poke it in the ribs. And here's the kicker. Even if the probe never reaches its black hole, even if it dies halfway, the technologies we build along the way will spill into everyday life. Because missions like this aren't just about data, they're about invention. And that story, how black hole science trickles down into earthly gadgets, that's worth its own chapter. If you've been listening so far, you might be thinking, okay, neat story, But why spend €1 trillion flinging a paperclip at a black hole? That money could buy schools, hospitals, or at least fix the pothole in front of your house. Here's the thing about impractical science. It almost always comes back around to save us in ways no one expected. It's the boomerang of human curiosity. You throw it at the stars, and one day it lands back on your kitchen counter as an app, a material, or a medical breakthrough. Take the Apollo missions. We didn't go to the moon to invent Velcro, freeze-dried food, or the computer chips that now run your phone. But that's what fell out of the toolbox along the way. Giant space projects force us to solve problems, and those solutions rarely stay in space. This black hole mission would be no different. Think about the technologies it demands. Laser propulsion. If we can scale that, suddenly interstellar travel shrinks from millennia to decades. But even before that, lasers could revolutionize satellite launches or even provide clean energy transmission on Earth. Your power grid might one day be steadied by technology born from black hole chasing. Miniaturized deep space instruments. A craft that weighs a few grams but still does science. That's a revolution in sensor technology. Imagine medical implants, environmental monitors, or disaster response drones using the same breakthroughs. Radiation-resistant materials. A nanocraft that survives decades of cosmic ray bombardment would be wrapped in materials tougher than anything we use today. Those could shield astronauts, satellites, nuclear reactors, maybe even your future car battery from degradation. Data compression and long-distance communication. To whisper across 25 light-years, the probe would need communication protocols far more efficient than our current ones. Guess what else benefits from that? Every text message, every streaming service, every attempt to video call your grandmother without it freezing mid-sentence. It sounds silly, but history proves it. Chasing impossible dreams gives us very practical tools. The black hole probe is, in one sense, an expensive physics experiment. But in another, it's an R&D engine for the entire human race. So yes, maybe your Wi-Fi will be faster one day because some lunatic scientist decided to throw a paperclip into a black hole. And wouldn't that be the most human thing ever? Of course, all this assumes we can even start the mission. And that requires patience, mountains of it. Because before we can light up the lasers, we have to find our target. And finding one nearby enough to matter may take years, maybe decades. Which brings us to the waiting game. So here's the uncomfortable truth. All this talk about nanocrafts, lasers, and physics jackpots doesn't mean much if we don't actually have a black hole within reach. And right now, we don't. The closest confirmed one, Gaia BH1, is way too far. Our dream probe would never make it there in a humanly relevant time frame. Which means the whole plan is theoretical. A castle in the clouds. A paperclip without a dartboard. What we need first is discovery. The detection of a stealthy, quiet, nearby black hole hiding in plain sight. And that, frustratingly, is something we can't just order on Amazon Prime. The good news? Astronomers are building the tools. The next decade will bring a wave of all-sky surveys, instruments designed to track the tiniest stellar wobbles and the faintest gravitational lensing events. They're essentially black hole sniffers patiently scanning the night for clues that an invisible monster is tugging on its neighbors. But this takes time. Years of collecting data, refining algorithms, ruling out false positives. Astronomy is less like an action movie chase and more like fishing in the dark with a net the size of a continent. Most nights, you catch nothing. Some nights, you get seaweed. And every once in a while, if you're lucky, you feel something massive bump the net. Until then, the mission waits, and humanity waits with it. But here's the thing, Waiting has always been part of the scientific game. Gravitational waves were predicted in 1916. We confirmed them in 201599 9 years later. Black holes themselves were theorized in the 18th century. We didn't photograph one until 2019. Progress is slow, sometimes maddeningly so. But when the payoff comes, it's world-shattering. And maybe that's the point. Missions like this force us to stretch our timelines, to think beyond quarterly reports, election cycles, or even single lifetimes. They remind us that some questions are bigger than us, and the answers belong not to individuals but to civilizations. That's why this mission feels less like building a spaceship and more like planting a cathedral. You begin the work knowing full well you'll never see the spire. But you start anyway, because you believe someone will. And that belief, that stubborn patience, is what carries science forward. Of course, belief alone doesn't launch a probe. For that, we need a roadmap, a realistic set of steps that can take us from wild PowerPoint to actual mission. And that roadmap, it's already being sketched. By now, you might be wondering, okay, this all sounds amazing, but how do we actually get from cool idea to probe launched? Science doesn't just leap, it stumbles, crawls, climbs, and occasionally faceplants its way forward. And a project this absurdly ambitious needs a roadmap, one that stretches across decades. Luckily, people have already started sketching it. Step 1. Find the target. No black hole within 25 light-years. No mission. So the first order of business is astronomy. Build bigger surveys. Map more stars. Track every wobble and warp of light until one of them gives away the presence of an invisible monster. That alone could take a decade or more, but without it, everything else is wasted breath. Step 2. Prototype the nanocrafts. Before we fling one at a black hole, we need to make sure they even work closer to home. That means test flights in the solar system. Maybe a probe to Mars, or the asteroid belt. Maybe one flung past Pluto. Each attempt would stress test the sails, the radiation shielding, the communication system. Think of them as training wheels for interstellar biking. Step 3. Build the lasers incrementally. No one's building a €1 trillion array in one go. Instead, we'd start small. A few dozen lasers, then a few hundred. Each test pushes a probe a little faster, a little farther. Eventually, the array scales up to the monster we need to hurl a nanocraft across the stars. Step 4. Interstellar demos. Before we risk a 90-year mission, we try shorter trips. Maybe launch a probe toward Alpha Centauri, where we only have to wait 20 years for arrival +4 for data. If that works, confidence builds. Then, and only then, do we dare aim for the abyss. This staged approach isn't just about practicality. It's about survival. You don't bet your civilization's resources on one giant roll of the dice. You bet smaller first, learn from the losses, and build up until the impossible looks, well, just difficult. And while all this unfolds, there's a deeper layer to the plan. Something that doesn't get talked about in engineering documents, but lingers in the background of projects like these. The philosophy of time. Because the black hole mission isn't really about us. It's about who comes after. It's a relay race we'll never finish ourselves, a cathedral we'll never see completed. Which leads us to the most human part of the story. Why we bother to start something knowing we won't live to see it end. Let's pause for a second. Imagine pressing the launch button on this mission. You know with absolute certainty that you will never ever see the result. Not your children. Not even your grandchildren. By the time the probe's message makes it back, you'll be a name in an archive, maybe a statue in a dusty university hallway, maybe not even that. So why bother? Because this is how humanity has always built meaning. By doing things not for ourselves, but for those who come after. Think of the medieval cathedrals, projects that took centuries. The stonemasons who carved arches knew they'd never live to see the final spire touch the sky. But they carved anyway, because they believed the future was worth their labor. Or think of trees planted by hands that would never sit in their shade. The act wasn't selfish, it was generational. This black hole probe is the same. It's a reminder that science isn't just about answers, it's about continuity, about handing off questions like a baton in a relay race across time. Each generation runs a little further, then passes it on. And there's something strangely comforting about that. That even when we're gone, our curiosity keeps running. Our questions don't die with us. They live on in the instruments we build, the missions we launch, the notebooks filled with scribbled equations. Maybe the probe makes it. Maybe it doesn't. Maybe the data it sends back confirms Einstein, or maybe it tears his equations apart. Either way, we'll have reached further, dared harder than any generation before. And the ripples from that daring, technological, cultural, even philosophical, will outlast us. In the end, sending a probe to a black hole isn't just about physics. It's about faith. Faith that the unknown is worth chasing. Faith that progress outlives individuals. Faith that curiosity, once lit, doesn't go out, it just changes hands. So when the day comes that humanity finally does it, when the laser fires, the sail catches light, and that tiny craft streaks off into the abyss, it won't just be a scientific experiment. It'll be a love letter across time. From us to whoever's listening on the other side of the century. And maybe, just maybe, that's the real point. Not the answers, but the act of asking questions we'll never hear answered. Because that's what makes us human. Not the span of our lives, but the reach of our wonder.